Okay, so well, welcome back, everyone. So it's my pleasure to introduce Mohit Bansal. So Mohit um, got his PhD from Berkeley. He's currently a distinguished professor and the leader of the NLP group at the Computer Science Department of the University of North Carolina, Chapel Hill. So his research interests focus on multimodal machine learning, natural language processing, and he has a very distinguished career with different awards, best papers at venues like CVPR, and um, uh, also extensive service to the community and very many distinguished roles in terms of service to the community. And well, his talk here today is going to focus on, well, actually different things. So multimodal models, unification, evaluation of these models, planning agents as well. So let's give a round of applause to Mohit.
Thanks. Thanks for having me. Can everyone hear me in the back? Oh, I should mute myself. So somehow I can't find the mute button. Oh, it is mute. So, okay, I guess the speaker is on. I think it's the jet lag. But yeah, so thanks for having me. And yeah, so today I'll be covering three aspects of multimodal generative models. One is unification. The other is planning agents, specifically LLMs and their capabilities as planners and programmers to improve multimodal generation. And depending on time, I'll also try to cover as much as possible on evaluation. But my goal here is to give you sort of an overview of some of these topics and then facilitate more discussions because I'm around today, tomorrow, as well as Thursday. Okay, so yeah, this will be the talk outline. So like I said, we'll be having this journey on multimodal generative models and specifically trying to look at three things: unification, interpretable planning and programming, and lastly, evaluation. So the first part will be about unification or universal multimodal learning. And the goals here will be to increase their generalizability, shared knowledge, and efficiency. So I'll give you a little bit of, I think given this morning, like lectures, luckily I don't have to give too much background, but just very briefly, right, the whole idea of pre-training and then fine-tuning paradigm, I think I don't need to explain to this room, right, it's all around us now more than we want. But the idea here was, right, that the motivation several years ago was that the amount of data is very limited in downstream tasks. So pre-training, right, naturally enables much more data through natural supervision, self-supervision, right, clever ways of creating more pre-training objective data for pre-training objectives. So for language, you would do something, for example, back then, like text in Wikipedia, right, do a masked language modeling. I call it a fill-in-the-blank task, right? So kind of try to do a fill-in-the-blank kind of task and get a pre-trained model, and then you can fine-tune it for downstream tasks like sentiment analysis. Vision has been doing the same thing for a long time, right? You would do visual pre-training, for example, on ImageNet, you could have image classification. Now you can have patched reconstruction kind of pre-training tasks, and then you would do visual fine-tuning for downstream tasks. So the motivation I'm trying to give here is that if you have these separate, independent, pre-training of single modalities, then if you want to do multimodal tasks that naturally need you to be able to learn correlations and connections and alignment between multiple tasks, multiple modalities, right? The early ways to do this you would have this independent visual pre-training pipeline and an independent language pre-training pipeline, and then you would try to do a sort of post-hoc late fusion kind of multimodal fusion layers, right? And then try to go and use that for your visual question answering, visual navigation, visual grounding kinds of VL tasks. So obviously that's not ideal because you would rather have the model inherently from the very beginning, right? Understand, or force it to understand and learn relationships between the modalities. So LexMERT was one of the first sort of multimodal BERT large-scale cross-modal pre-training models. So this was around 6 years ago we started this, but the simple idea back then was that you would have the masked language modeling pre-training task on the language encoder side. You would have the masked vision modeling kind of pre-training objective on the object relation encoder, right? So back then it was not patch reconstruction, but it would be the same idea, but at the feature level, right? So you would have masked vision features and you could have region of interest features or positional features, and you would learn an object relation encoder. And then the most important third encoder, which was the cross-modal encoder, right, this would come in. And this idea here is that you're trying to have pre-training tasks, which are basically forcing the model to learn relationships between the modalities. So instead of just doing fill in the blanks on language or on vision, you you could imagine this as a multimodal fill in the blank task where you have to fill the gaps in the language side given the image and fill the gaps in the image side given the language, right? And you could also have things like matching, cross-modality matching, where you're given positive and negative pairs of images and captions, right? And you force the model to tell you which ones are the positive pairs or the negative pairs, so and so on. So this achieved pretty big gains and state-of-the-art on several vision language tasks back then, like VQA, grounded QA, multi-image relationship tasks like NLVR2. VisVis is like a visual question answering task, but with images uploaded by people with visual disabilities, so they can be out of focus, incomplete images. So this is not, again, the focus of this talk. What I'm trying to say here is that then I'm not exaggerating if I say that there's probably more than 2,000 models, right, since then, that have come up with specialized vision and language pre-training architectures. And by specialized, I mean different axes. It could be different architectures like single stream versus dual stream, attention methods being different, attention heads, objective functions, different encoders, decoders, output heads, all kinds of specialized modules being handled given the task, OCR, ASR, tokenizers, et cetera, et cetera. So that's sort of the motivation of the first part, right? Where I'll take you through a brief journey on progressively more unification for multimodal learning. And then in each of the next parts that I'll progress to, I will complain about the previous part, right? And motivate how we need more unification to reach the final step. So the first example in this unification story is VLT5. So this was the first unified model back again 4 years ago and published at ICML 2021, where the idea was basically, again, looking at these diverse vision and language tasks and specialized models for them, right? So for example, a VQA task would be something, and sorry for the slide blurriness, we tried various ways, but I think I'll send you the slides, but there's some sort of Zoom or projector connection thing. But if anything's unclear, let me know. But basically, the VQA side would be basically an image and a question. And then a very specialized model like MCAN, right, would go in and answer a multi-label classification task out of, say, a vocabulary of 2,000 answers. Image captioning would be different, right? Image goes to a longer sentence generation, for example, using BUTD or AOANet. Visual grounding is a very different task where given an image and a referring expression, right, you need to visually ground that expression. This is also known as visual pointing or referring expression comprehension or visual grounding, a lot of different names for this task. But you basically have to find that specific region, right, which this expression refers to. And then another very different task would be multimodal machine translation, where language 1 plus image as a bridge, right, helps generate language 2. So the motivation here was that, like I said, all these different tasks ended up having very specialized architectures to obviously get, right, the best benchmark performance and rank that you can get on the benchmarks for those tasks. So for example, VQA would have, right, these image features, the question features, go into a very specific vision language transformer, and then have something like a VQA head, a sigmoid over top K answers, and then try to do this as a multi-label classification task. For example, another task like visual grounding would do something different in its transformer, and then go to a region scoring head, do a softmax, right? So there were all these sort of very different specializations that people were converging to, right, to specialize on these tasks. So the goal here was, can we tackle all these vision and language tasks with a single objective? So we said, yes, let's do this as conditional multimodal text generation. So the idea here was that let's see which tasks can be converted to text generation, right? So multimodal LM, which is, again, I'll call it a multimodal fill in the blank task, is natural here, right? A dash is dash over fire hydrant. So the model then needs to generate the two fill in the like the blanks, right? Man and jumping. For VQA, instead of doing multi-label classification over 2,000 vocabulary answers, right? You could generate the answer piece by piece. Visual grounding is more interesting. You're not predicting the box ID, but you actually try to generate the ID of the box, and then later even the coordinates, the x1, x2, y1, y2 coordinates can be generated as text. And then other things are easier, right? Image text matching. Instead of classifying it as true or false, you can try to generate it through the autoregressive text decoder. So this was the simple idea of VLT5. Basically, you want to feed in the task prefix. This was an early example of task prompting. Then you feed in all the features from the language side, all the features from the vision side, and then you feed all this into a bidirectional multimodal encoder. And then you want to have all the outputs generated through this autoregressive text decoder and treat this as a multimodal conditional language modeling task. So I'll tell you briefly again how a lot of these blue specialized tasks at the top, right, can be handled with the same architecture at the bottom in VLT5, right? So we already went through VQA and visual grounding, And at the bottom, right, now this can basically be just this exact same single transformer with shared parameters and handling both of these tasks as multimodal conditional language modeling. But then even more different tasks like NLVR2, which is a binary classification task for multiple images. So an example could be there are 3 images, and the model needs to figure out whether there are only 2 images in which a red glass is next to a yellow ball, right? So these are multi-image relationship classification tasks. So here too, instead of having this specialized architecture with multiple transformers and an NLVR2 head, VLT5 can just handle a sequence of multiple image regions from multiple images, right? So it can handle multi-image tasks easily, and then have the task name and the text part of the input. And then also things like multimodal machine translation would be similar, where you would basically feed in the vision features, the names of the languages to be able to do zero shot, right, bridge translation too, and then the language input, the text input, right, and then output the second language. So I'll not go too much into the result details, since I'm trying to cover a sort of journey of progressively more unification. But the 3 main results here, and we can discuss more offline. The first result was that compared to all the specialized models for these 7 or 8 different VQA relationship, referring expression, captioning, multimodal machine translation kinds of different discriminative and generative tasks, compared to all the specialized individual models for these tasks. That's why you can see a lot of dashes, right, in the previous work, because they're all sort of specialized for 1 or 2 tasks. So VLT5 with a single architecture, right, can maintain most of the performance. And then the second more interesting part is that it can also then reduce its parameters to 14% because it's the same architecture. So with 1/7 of the parameters, it can still get reasonable performance and not drop too much. But the third advantage is that it also is able to perform better on rare and unseen categories, because by definition, it's generating text as opposed to classifying. So this is a big problem in tasks like VQA, where there's even specific different splits for unseen or rare categories, right, which the model is not trained on. So there's been a lot of follow-up useful works on unification since then. I'm sure some of you played with SimVLM, Flamingo, OFA. So that's sort of the motivation of unification. Now, for the next part, let me try to, like I said, complain about the previous part, right, as I progress through more unification. So for VLT5, right, what we can say is that it was good that it unified the outputs as text. But if you notice the left side, right, the image encoder was still separate, right? So you still had to have a separate image encoder and the text going in through a different text encoder. So in TVLT, which was NeurIPS 2022, which we call textless vision language transformers, we tried to understand whether we can try to have the same exact sort of pre-training objective and the encoder for both language and vision modalities. So the way we did this was we said, let's try to remove all dependency on text. So it's a textless vision language transformer. And the motivation came from the fact that one of the main goals for this model, for example, would be video and language modeling. So if anyone has worked on videos and language tasks, the very big problem is here that there's a lot of noise between the alignment of the frames in the video and the ASR output, right? The sort of subtitles and the text that comes out of the ASR. And there's also a lot of tokenization issues, right? So this is one of the motivation that made us think about this. And we said, what if we directly start with audio and treat audio as images? Right, so the idea here was that for the image side, which are the frames of the video, you're already doing masked image reconstruction, right? So that's the pre-training objective. You take out pieces of the image and you ask the model to fill them back. So we said, let's try the same thing on the audio side. We take the spectrograms of the audio, we try to take pieces out of it, and we try to ask the model to learn to predict these pieces back, right? So this is another way of trying to treat these two modalities together with the same encoder as well as the same parameters and the same pre-training objective. Right, so in summary, it's a unified vision transformer style patch embedding task for both video and audio inputs. We have a masked auto-encoding style encoder-decoder, so this allows you a multimodal joint encoder, and the decoder weights are also shared, right, and they reconstruct the two modalities. So the two objectives, as I mentioned, for the first one is the masked auto-encoding, and the second one is the common contrastive learning kind of objective, right, where you have positive and negative video and audio pairs. So in terms of the results briefly, this was a pretty surprising result to the community back then, where we said, we showed that our just audio-based textless vision language transformers without any kind of ASR or tokenizer or other text module dependency performs competitively with text-based models. And we tried very different tasks like image retrieval, video retrieval, visual question answering, all the way to multimodal sentiment analysis and emotion analysis tasks from CMU, where this, in fact, was even better, right? Because you're getting the additional audio features. But the main advantage here, like I said, was that it's 30 times faster inference and 1/3 of the parameters, because you are removing dependence on all text modules while also sharing the encoder and the parameters. Now, the next step here that I'll complain about is that even if we unify all of these vision, language, VQA kinds of models on the input and output side, this is still not solving the real world issue where if you're trying to do any real world application of vision and language, this is not how we get the inputs and outputs, right? No one gives you a clean image and a clean question and say, okay, like let me get the answer for this setting, right? The idea here is that modalities exist in the wild in terms of websites, right, with different kinds of images and paragraphs and footnotes and headers and logos, right, and also in things like publications and in utility bills, right? So these are the sort of real world document processing multimodality tasks in which, in the way that modalities exist around us, right? A very concrete way to think about it is if anyone works in these with these models, you will notice that even the best models cannot even handle a slightly different situation like multi-image inputs. They're all so sort of trained to focus on one, like we given one image and one question, or one input text and one input image, that even like new models had to be created just for a simple thing like having two images instead of one, right? Or even like having text in very odd places in the image, right? Or in the document, like on top of the image versus bottom, right? Even those things we cannot keep specializing for each of these situations. So the next step, which was UDOP, Universal Document Processing, in CVPR 23, we said, can we also treat layout as another joint modality like image and text, right? So the idea here is that we should be able to have a model that can automatically learn different kinds of layouts of publications, websites, utility bills, and whatnot, while basically while also learning OCR kinds of tasks, right, jointly with the model, and without having layout-specific architectures. So it's a very simple idea the way we do it. What we do is, again, I'll keep calling this a fill-in-the-blank task, right? So the idea here is that now when you're pre-training the model, you're not just teaching it to remove a piece of text and predict it back. You're not just telling it to remove a piece of an image and predict it back. You're actually now also going to ask it to do it jointly with the layout. So what that means is that I will basically ask the model to not just predict the missing text piece, but also its location and its layout, right? And also the same thing for images. So if you think about it intuitively, this is teaching the model both the layout of the document, but also very interesting things like the text is basically a footnote or a header or a caption, right? Because as humans, if I give you two pieces of text, one is from a caption and maybe one is from a footnote, most of you will be able to differentiate, right, from your own papers. So that's the basic idea, that if I'm also doing masked language reconstruction or masked image reconstruction, but forcing the model to also tell me its location and layouts and the x1, x2, y1, y2 coordinates, that's not just teaching the model to be layout independent, but also teaching it the location and the kind of text and images that occur. So that was the only sort of simple innovation here. You basically, if you see the color-coded things here, the green, yellow, and purple are the independent single modality, right, pre-training reconstruction objectives. But then we also have the yellow ones, which are the mixed reconstruction. So you're doing text reconstruction with layout. And the other interesting thing, so basically, first of all, in terms of results, this model, right, just with the simple intuition of learning the layout as pre-training, gets state-of-the-art rank 1 on this very interesting benchmark called DUE. So this is the most sort of widely used document understanding benchmark. I would definitely encourage people to look at it. So it's very interesting. It has diverse data domains like finance reports, academic papers, websites, right? And it also covers various very different kinds of tasks like direct visual question answering on a document, entailment in tables, right? Question answering on tables, document information extraction, right? So all kinds of diverse tasks, but directly at very diverse layout multimodal documents, right? As opposed to already assuming that the model will know what exactly is the input and where is it located. And the other big thing about this model that made it so powerful was that it's not just an understanding or encoder model, right? There's a lot of power on the decoder side where we are actually teaching the model to be able to do very fine-grained edits in the document. So basically, I can take the logo and I can ask the model from the left side to go to the right side, right? Replace the title with some exact text that you want, and it will imitate the exact same printer ink, the exact same format. It can add something where you add a box. It can add whatever text you want, right? It can replace text, all of these things. And as you can imagine, this decoder is not released because the job of this decoder is to improve the understanding model, not to be misused, right? But yeah, that's a different talk. Okay, so that's the third part of unification, right? So I went all the way from unifying the outputs to the inputs to the layouts, right? Because I don't want to use models where I have to keep telling it that, no, now you don't expect one image, you need to expect two images. And then it tells me, wait, I don't know how to do that. So this is not just two images, right? But any amounts of images or text or signatures or serial numbers or logos, right, in any layout possible. But this is still missing a big piece, right? So if I had to complete the story of unification, one big piece missing here is that all of these models still have very well-defined input modalities and output modalities, right? I have a very specific, every model has a very specific knowledge or a requirement that the input will be image plus text and the output will be a video, or the input will be video plus audio and the output will be an image, right? So can I have the best power of unification, which is generalization to unseen modality combinations? So this is what we called CODI, composable diffusion on any-to-any input-output modality generation, right? So this is a sort of new paradigm called any-to-any, which you'll hear a lot around you now. But the basic idea is that it should be able to take any input combination of modalities that it has not even seen during training and generate any output combination without relying on training data for those combinations, as well as not having exponential training objectives, but only linear. So this is the idea of CODI at NeurIPS 23. Let me give you a short demo first. So like I said, CODI can jointly generate any-to-any combinations, right? So first, let's assume you have a storyboard, right? So in your laptop, you have a folder with some images, some text pieces, and some audio clips, right? So think of it as a storyboard where people are basically taking different kinds of modalities and trying to generate stories out of it. So what I can do is I can basically have this image, right? And I can have a text saying, so this is a New York Times Square kind of image, right? And then we have a teddy bear on a skateboard, just as an example of the text. And then this audio clip might be rain sound, right? So now what I can tell CODI, okay, so there'll be two audios now. So I'll tell CODI first, maybe take a single modality to single modality task, right? Take the audio track and maybe audio to text. Now I can have two arrows. I can say take the image and take the audio clip, which is the rain sound, and generate another audio. Yeah, figured it out. Thanks. So I thought I'll be able to get away with it. Yeah, so then if you follow the red arrows, right, I can tell CODI, and again, sorry for the blurriness, but the slides are very high resolution, so I'll send those. But yeah, so then what I can say is, hey, now take this audio clip and this image and just figure out how to mix the diffusion latent variables, and I'll give you the little bit of technical details next. Mix the latent diffusion variables to basically create another audio clip. So now what it'll do is, so I don't know how clear the audio is in the room, but what it's doing is, I'll also send you the website link later, but actually it's on the slide, is that it will now create an audio clip not just with the rain sound, but also the street noise, because it learned that latent variable from the busy street, right, on the image side. So I can also tell it to do more complex thing, right? I can say, take the 3 purple arrows, right? So now take the image, the text, and the audio, and generate an image plus text, right? So what it does now is that it takes the sentence and converts it to an image, where it shows the teddy bear on the skateboard. It keeps the image background of the street, busy street, New York street. And if you see, the floor is wet because of the rain from the audio clip, right? So these are 3 LDMs, latent variables being mixed. Now I can be even more complex. I can say, can you generate a video and audio for these 3 inputs? So the audio is important here, right? So let me mute myself first. So basically the point here is that first of all, you will see the busy street. So let's do one by one, right? So the image input is being seen in the background of the video, right? The same kind of New York Times Square scenario. The teddy bear sentence is coming in as an actual dynamic teddy bear movement. And the most important part is the audio, where now if you use the website later with sort of your headphones, you will hear three sounds. One is the rain sound, obviously from the audio clip, the street noise from the image, but this time there's a third sound because of the teddy bear, like the skateboard clicking sound, if you can hear it. So that's sort of the main goal of Cody, right? So let me move on to some of the technical details. So this is basically the idea that can we have a new kind of generative model that can take any combination of input modalities and generate any other combination, right? So think of it as a many modal kind of storyboard. But the capital BUT, right, is that this is with significant costs, right? Because the number of input-output combinations will scale exponentially, as well as training data, right, will be missing for most of these combinations. So that's sort of the main innovation here, that can we have a simple bridging alignment where we try to show you how to get linear number of training objectives and also not block on things in the training data. So there's three stages: composable, conditioning, joint generation, and inference. Very briefly, in stage one, we have a latent diffusion model for each modality first. So the important thing is they are trained independently first so that you can ensure high quality generation for each modality. And then for conditional generation, for example, audio plus language to image, the input modalities are projected into a shared feature space, right? And then the output LDM is basically doing its attention, right? Getting its attention or paying attention to this combination of the input features. So this is to allow the input mixing. And the output side, you first add a cross-attention module to each LDM, and then we have this environment encoder, right, where its job is to project these LDM latent variables into this mixing space, right, where you can mix the output modalities. So yeah, so this is the basic idea. This was a collaboration with Microsoft through one of my students. So let me give you a couple of more examples. So audio plus image to text plus image. So basically I can give it a clip of, say, this piano sound and this forest image, right? And then ask it to generate a text plus image. I can give it text plus image to video. So eating on a coffee table is the text, and maybe the image is this kind of panda image. So then it can try to basically have the same subject, right? But doing the thing mentioned in the text. Okay, so this is still not the last piece in my sort of satisfaction of unification. So then the thing you can complain about Cody, one, is that this is not how I would like to talk to a model. Image plus text goes to video plus audio, right? So the sort of one of the final pieces here would be whether you can actually talk to Cody 1 through language interactively and iteratively, right? Can you actually have multiple iterations through natural language and have Cody as a backbone by connecting it to an LLM, which allows both interactive any-to-any generation, but more importantly, interleaved also, right? Which means that every prompt can actually be mixing multiple modalities together. So this is recently at CVPR this summer. So let me give you only a demo for this one. So the first input could be that I have the human sort of interactor is basically giving, again, you have a bunch of images, right? And and a storyboard, right? With audio clips, images, text pieces, and you're trying to create a new sort of complex modality story with it. So you can say, learn the subject in this sort of maybe your favorite pet dog's photo, and then generate with it on the concept represented by some photos that you found on some vacation, right? With a circular arc. So then it will try to have the same background with the image. Now I can say, can you edit this image in the vibe of an audio clip, right? So in this case, it's a rain sound, so it will make the same image look misty and the floor wet. Now I can say, what's the edit bit? So it can also do sort of this analogy reasoning, right? A minus B plus C. So what's the edit between A and B? Apply this same subtraction, right, to the given image. So it will figure out that there's a season change. And so it will basically make the same image right now with fall season, and it will also tell you I changed the season of the scene. So this is sort of one capability. There's several other capabilities, right? So you could do things like I said, exemplar learning. So A minus B plus C, right? So king minus man plus woman is equal to queen kind of analogy reasoning that we had very early on in NLP deep learning kind of embedding community. Right? You can also do things like the same exemplar learning or analogy learning, but for other modalities. like street plus rain minus street will figure out rain, and then add that to train. So train plus rain. It can also do things like compositionality. So this is a reasoning example, which is one of my favorites. So basically, it can also take like given X, Y, and Z, what happens next. It can do even multimodal reasoning. So given these video frames and generate the sound and image for it. So what happens next? Same thing for. And it can do composition, right? So A plus like A on B, right? So if you have two images and you want to compose them, but with a specific preposition, right? Through the language model's planning capabilities, which I'll get into in the next part. So anyway, so this is sort of the last slide for the unification part. So this is something hot off the press where this is another any-to-any example. So the previous any-to-any example was for combining modalities. This is called control adapter, where the idea is, this is a big problem in the video generation community right now, where you might have a lot of user-given controls. So things like depth maps or canny edges or user sketches or scribbling, even pose information or segmentation, right? So the problem is that there are such diverse video generation backbones and such diverse control nets for these user-defined controls, and they don't talk to each other. So control adapter is the first sort of open source academic effort, right, where we are trying to have a very efficient way to convert any user-defined input control to a control net, and then through very efficient adapter training, be able to add it to any kind of video generation backbone. So any kind of input control can be applied to any kind of video generation backbone. The best part is it's only 12 GPU hours. So like in maybe around 8 to 16 800s and 12 GPU hours. The second advantage, it can do multi-condition video control, which is a patch level mixture of experts. So we created a new kind of mixture of experts at the patch level, where it can also handle multiple conditions in parallel. Like one user might give it a depth map, the other one might give it a sketch, and you can incorporate both of these into your final video generation. It can also handle sparse video control, where you might have missing frames, and image control. Okay, so this was sort of the unification story of the talk. Now, the second equally sort of related and important part is the black boxness and the lack of control and interpretability, right, in multimodal generation. So in the second part, what I'll talk about is how can we make multimodal generation interpretable, not just for the model, not just for humans, but actually for the model itself, right? The problem is that these multimodal generation models, there have been recent studies that have shown that they cannot even understand themselves what they generated. Like if you take their generations and ask them to actually do classification or understanding tasks on it, they themselves really don't know what they've created. So it's not just interpretability for humans, but also for models itself. More importantly, control, right? I'll show you how these LLM-based planning agents can allow you to control image and video generation, as opposed to just let me keep trying different prompts and get lucky. Right? And then also more faithfulness to the input prompt, including out of domain and out of distribution scenarios. So I'll cover the first two parts a bit more detail, and then last one is a nice example from the education community. So yeah, I'll talk about planning for image generation, planning for a very complex task like long, consistent video generation, and then some open domain diagrams. So coming back to the background that I was just mentioning, or the motivation, right? If you have this is a toy example. Suppose you have a prompt like 2 Pikachus on a table, right? Or a truck is behind a motorcycle. So all these current sort of image generation models, the problem is that you will see some very nice images, right, pop up, but then very soon you'll realize a lot of important semantic issues, right? There's no fine-grained planning or control. There's no interpretability behind the generation process. And there's also a lack of faithfulness to the input, right? Both in terms of positive and negative hallucinations, as well as out of domain scenarios. So I'll give you more details next. So what we do in VP Gen at NeurIPS 23 is visual programming for image generation. And the idea here is that you have, for example, the prompt is 2 Pikachus on a table. So what you'll teach the LLM is that, hey, take this prompt and first, given this caption or prompt, determine the objects and their counts to draw an image, right? So it will first convert 2 Pikachus on a table to Pikachu 2 and table 1. Then the more interesting part is the next step, which is layout generation. Given this caption or prompt and the objects that you counted, now determine the actual coordinates, right? The bounding boxes of these objects. So here's where some of the sort of language knowledge about prepositions and other things starts coming in, where since it says 2 Pikachus on a table, it will basically learn that these coordinates that it's generating for the boxes, the coordinates, the average y coordinate for the table box will be lower than the average y coordinates, right, of the two Pikachu boxes, because it's on as opposed to under. And then the third part will be given these boxes, it will try to fill in. Right? This is called in-painting or infilling, right? So layout conditioned in-painting modules will be used to actually fill in the information jointly. So in terms of the main results here for VPGen, what we showed is that actually for three very important skills like counting, spatial relationships, and scale, VPGen is much better than most of the Stable Diffusion 1.4, 2.1, right? All the sort of top models back then. And the idea here was that first, I mean, I'll give you three examples, right? One for each. So if it's about counting, right? If I ask Stable Diffusion to give me 3 boats, like the boats look very nice, right? But then suddenly, like very quickly, you'll realize that there's no notion of 3 here, right? So if you're doing a planning based approach, you're already forcing the model to first generate the layout boxes, which already are faithful to the prompt part of 3. And then you do the infilling to create the boards. Even more tricky is spatial, right? So a truck is behind a motorcycle. You can see that the spatial results are even lower than count, right, for the baseline. So only 22, 20 to 30%. So these are things like a truck is behind a motorcycle. This is what Stable Diffusion would do, right? But if you force the model to do planning first, it will already make sure that the bounding box for the motorcycle is in front of the bounding box for the truck, right? So the truck is behind the motorcycle. Same thing for even more complex cases like scale. And all of these, by the way, can be out of domain or unseen scenarios, right? So if I can say a remote that is bigger than a cat, no training data or right, the training image distribution will have this. But since you're forcing the layout plan first, right, you can in fact make sure that the remote box is bigger than the cat box. And the best part is you have human in the loop control. So even if you still don't like it, right, you can go and first change the bounding box plan and then ask the model to regenerate the image. So these are sort of the three advantages, right, of this whole paradigm. That one is that the model and humans both understand the actual process, right, behind the generation. The second is that it can handle out of distribution unseen cases. And third, most importantly, it gives you more explicit control over the image generation process, which in turn, right, helps you to not just keep trying prompts randomly, but more importantly, also tells you what are the current errors or limitations of the model, right, to be able to improve in your next iteration of modeling. And now I'll give you an even more complex example, which is for long video generation. So this is the first paper that tried to tackle like long, consistent video generation. This was around 9 months ago. And the idea here is this is all academic scale, right? 4 A100s or 8 A6000s. And the whole idea was, can we use LLMs as planners for long videos such that we can use the idea of co-reference and layout generation to understand what should be consistent across the video and also have very fine-grained layouts. So let me start with a toy example, and then I can show you some real examples. So if the prompt is a hungry cat is finding food, right? So the idea here would be that the first stage, which we call the video planner, will try to first break this prompt into 3 subscenes. So maybe it will predict that the first scene is a cat is lying down on a bed, right? So for that, it will first generate the sub-scene description, but it will also generate all the entities in this scene, as well as their bounding boxes, as well as their color coordinates. So it will actually make sure that it learns that which entities belong to the same co-reference cluster, right? So the idea here is it will predict, okay, let me find a cat and let me generate a bed. And also let me make sure that the y coordinate of the cat, right, on average is higher than the y coordinate of the bed because the relationship is on a bed, right, not under. And it will also predict the background. Now it will generate the second scene and say, then she gets up, right? Because the hungry cat is finding food. So maybe the next scene is that she needs to get up, right? To go to the kitchen. So then again, it will generate the scene. It will generate the bounding boxes and the entities. Now, currently in this toy example, the entities are the same, but the coordinates have changed because through the language model, right, it understands that when something is getting up, it will learn that the coordinates of the cat need to change such that the y coordinate becomes longer, right, and the x coordinate becomes smaller. And the bedroom is still the background. And finally, it might generate the third scene as she goes to the kitchen and eats a snack. Now it will predict that, okay, there needs to be a new entity, which is the snack. So this is, think of it as a co-reference resolution scenario, right? I don't know how many of you worked on co-reference resolution. It was definitely more of my grad school time sort of popular task, but it's a very important task, right? The idea there, one of the main models to do that would be that when you get a new entity mention, right, like he or she or they, right, you need to predict whether this belongs to an existing cluster of entity, right, an entity cluster, right? Versus should I start a new entity cluster here for this mention? So same thing we are doing on the video generation side, right? For each scene, when it predicts the mentions, right, of these boxes, it needs to also predict whether this box already belongs to a color that exists, like the cat, or this is a new entity cluster for, say, the snacks, which is red. And so then this is the plan. And then the second part is the video generator, which takes this whole plan of all the bounding boxes and the shared colors. And then it takes a single scene video generation model. It takes its spatial temporal blocks. And the only thing it needs to do is we introduce these guided 2D attention modules, where its job is to basically be able to force the model to respect the layouts, the bounding boxes that we forced it to generate in the video. So the best part is that it's very efficient, like I said, academically, like I said, 8 A6000s or 4 A100s, because we are only updating these guided 2D attention modules, and everything else, right, is frozen from the single scene video generation model. And the other best part is that all the parameters are shared between all the bounding boxes that are the same color, right? Because this is for consistency. So now let me show you some more interesting examples. So here are some basic understanding that the model learns of things like, say, basic physics, right? So if I'm saying a stone is thrown into the sky, I mean, this is repetitive. It's not going back and forth. It's just repeating the same frames. But the idea is that I threw the stone up, so it knows that it needs to bring it back. There's also a perspective kind of understanding. A car is approaching from a distance, so it's learning to zoom in as the car approaches. It also has some basic understanding of static objects versus dynamic objects in terms of the camera motion, which is a very big deal in video generation, right? So for static objects, it's learning that, okay, the bottle will stay static, right? But I will move the camera around. Whereas for dynamic objects like planes, both the object and the camera can move. Now let's look at more end-to-end examples. So it can handle two things, right? It can actually handle, obviously, if you give it the whole story, right, piece by piece, it can actually take that. And the left side is the single scene sort of models, right? Whereas this is sort of the right side is what the video director GPT is doing. And the main two things that you'll see here is one is you will see that it can respect very unseen kinds of layouts that have never been seen before, right? No training videos have mice reading books and holding petals in their right hand and so on. So you'll notice that it's like you see this frame currently, right? So the petal is exactly in the right hand. The reading of the book is very natural given the small compute scale, right? And the second very useful part that we are focusing on is that the mouse is consistent, right, across the whole video. So those are the two things, right, that are the innovations here. Obviously, now you can also do this harder task where I don't even give it all the sub-scenes. I just give a high-level scene like make a strawberry surprise, and it can automatically first break it into a whole story and then generate, right, each scene from each sub-sentence. A more important feature, in my opinion, like I said in the very beginning, is that this whole paradigm of LLM planning agents for image or video generation allow human-in-the-loop control, right? So it's not that I will just keep trying different prompts or like try to find a prompt optimizer, right? I can actually go inside the generated video, and if I don't like certain bounding boxes or certain parts of the plan, I can make the horse smaller. I can change the background to a grassland or a night street, right? So this is sort of the way you can actually go inside the process, right? As opposed to just having only access to the prompt level, which, trust me, is like a very shallow and sort of very inaccurate way of like, there's only so much you can do with a prompt when you're trying to do tasks like video generation. And then the last advantage here is user-based, like I said, input image, right? So you can have different kinds of user-defined inputs, and you can generate the same story, but with your favorite pet cat photo or a teddy bear photo and so on. I mean, there's also people photos here, but we are not trying to, like for ethical purposes, I think we are mostly sticking to animals and stuffed toys. And the good thing is, like I said, the people have also taken this work and scaled it to many, many more GPUs, right? And you can also make the visual quality also higher. But our goal, like I said, is to actually have the compositionality and the layout and the consistency, right, fixed. So this is just the first half of the paper. Like most actually of our time, we also spent half of our time or more on different kinds of metrics, right? So this whole area did not have any metrics 9 months ago. So we came up with a lot of different benchmarks, prompt sets, as well as metrics to have basic things like skills, counting skills, spatial skills, skills in videos. Even basic things like the direction of the action or movement was not being measured, or there was no benchmark for it. So we have a new benchmark called action bench direction, We also have things like FVD, FID, but new metrics about consistency, and also a setup for human evaluation. So if you're interested in this area, I would encourage you to talk to us, and also like feel free to play with these data sets and metrics. And then a very related example to what I just talked about, we have this NSF AI Institute on Education. And so there is a big demand for right, teachers to be able to have tools where, again, very importantly, with teacher in the loop, right? Not teacher replacement, but with teacher in the loop, right? Is there a fast way to be able to generate very complex descriptions of things like diagrams into actual visuals diagrams, right? That they can show students, but being realistic and being able to fix them sometimes, right? Because they'll not be perfect. So think of it, complex diagrams like a diagram showing the Earth revolve around the sun 4 times, one of each solstice and equinox, blah, 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 right? So what it needs to do is the diagram planning stage first converts it to entities, their locations, and in this case, also very dense arrows, right? So diagrams have this very complex additional factor of very specific arrows going in very specific directions and connecting very specific like subparts of the dense layout. And then the second stage would be diagram generation, converting this plan to an actual diagram. So like I said, the best part here is that it allows teacher in the loop kind of editing, where first of all, it's open domain. So if you read the paper, we have shown that this can be done on PowerPoint or Inkscape or any kind of platform you want. And then the more important part is, this is not just directly generating the diagram and then you keep fiddling with the prompt, right? No, it's actually showing you the plan, right? The initial plan before doing the generation. And this plan can be on PowerPoint, Inkscape, or whatever platform you want. So the teacher can go in and say, okay, I wanted to make this box a little bit bigger, and I want to bring this box a little bit downwards. And then you can just send that plan again and regenerate the new image, which is like the better plan, that better image that you wanted. So that's sort of my proposal, right, of like human in the loop, sort of more controllable and interpretable image and video generation. The last example in this part of the talk, and then I think I have around 5-6 minutes for the evaluation side, is I think this will be also pretty interesting to a lot of people in the audience. So this is a very sort of big paradigm where we are trying to ask, can LLMs actually help generate data, right, for very targeted improvements of any kind of agent. It can, so in this case, we have shown game agents. We take things like Minecraft and these kinds of games, and we take the best, say, RL agent in that game. And then we ask the RL agent to send its weaknesses to the LLM, right? What are the skills that it's bad at? And then the LLM's job is to create diverse new targeted environments of the game such that the agent can play in those new games and actually make those very specific weak skills stronger. So it's a very data efficient, targeted way for making your current task agent better by asking the LLM to generate data specifically for those weaknesses. So that's the simple idea. If I go into a little bit more zoomed in, so this is known as environment gen, NGen, LLM guided or LLM planned adaptive environment generation for training agents, right? So the idea is you have a small RL agent, and it can be any actually agent, right? It could be any task, model for any task, right? And then you would basically ask the agent to share its performance with the LLM. Some fine-grained sort of feedback goes to the LLM. It uses this feedback to generate new kinds of environments, right? Using, say, JSON files or other programming formats, such that then you send these environments back to the agent, right, to train on. And then this cycle keeps repeating n times such that the weaknesses keep changing, right? And harder things come up as weaknesses, and the model keeps generating targeted games for the model to play in. So yeah, so this is also pretty recent, so happy to chat about it. And then let me keep a few minutes for the last part, which is the very tricky problem of evaluation of multimodal generation models. So a lot of you have worked on text generation, right? You know already how sort of an open challenge it still is after 20, 30 years. This makes it even more challenging. So two basic examples I'll give of some of the progress we've tried to make in evaluation of multimodal generation. The first part is VP eval. This is actually the same paper as VP gen, right? So we showed how to do visual programming to improve both image generation as well as image generation evaluation. And the second part was basically the first paper to actually have concrete metrics for image generation, both from the skill side as well as social bias side. So I'll just give these two brief examples. For VP eval, the motivation is very similar to VP gen. It's all black box, right? Current evaluations, you'll send it to Clip or Blip 2 or whatever, and then you'll get some random score like 0.793. The problem is, first of all, you don't know how this score was computed. You also don't know how does this compare to, say, 0.78 versus 0.79 versus 0.3. But more importantly, you want to know what are the problems with the model so that you can actually improve it in the next round, right? As opposed to, okay, I'm happy because I got rank 3 on the benchmark. So it's a neural modular approach again, right? Neural modular networks, where imagine that you basically have all kinds of experts, right? So you can have experts for different things that need to be evaluated: object detection, object count evaluation, textual evaluation, OCR, spatial evaluation, right? So just to give you one example, spatial evaluation would be something like X is the right of Y. Object 1 is right of object 2. So then this module will make sure that the X coordinate, right, of the second object is higher than the X coordinate of the first object. If it was up and down instead of right and left, then it would be checking the Y coordinate. And if it was behind and front, then it would be checking the Z coordinate, right? Same thing for scale. It would check the area of the objects. So first you have these modules. Now, given this very long and complex prompt in yellow, the description is basically a white slope covers the background, while the foreground features a grassy slope with several rams grazing and one measly underdeveloped evergreen in the foreground. So the job of VP eval is to basically do visual programming. It will take this prompt and convert it to a program where each sort of property is being evaluated independently. It needs to check the presence of RAM, presence of evergreen, count of RAM should be greater than 1 because it says RAMs, not RAM, several RAMs. Count of evergreen should be exactly 1 because it says one measly evergreen. And then whatever else it cannot convert, it goes to this miscellaneous category of converting it to free-form questions. So what is the foreground? And the answer, it would become a VQA task. So the best part here is now you can actually execute this whole program, and you can actually see which parts of the generated image were problematic, and also with actual explanations, textual explanation, right? So it will actually tell you that in the presence of RAM was incorrect. No RAM was found in the generated image. Evergreen was found, so that's correct. You get credit for that. But then you get a penalty for having 8 evergreens, even though the prompt asks for 1. And then also the last one can be VQA, right? What is in the foreground? A grassy slope. So that's sort of, there's more very detailed results in the paper where we show that it's better human correlation, right, than other metrics. But the bigger part was the interpretability. Now let me come to the second. So let me come back to the VQA part, right? So the last point that I showed has this issue that it's basically a VQA task. Now you're giving too much power to a VQA model to open-endedly create questions, right, to evaluate generated images. And I'll show you the problem here. So this is a collaboration with Google at iClear 24, where we showed that if you just let a VQA model roam freely and widely on evaluating generated images, there's a lot of issues like complex non-atomic questions. It will generate questions like, is there a red motorcycle? That's a useless question, right? Because it can say motorcycle is yes, but the color is no, right? So it's non-atomic. It can also have invalid dependencies. If I already said no to a motorcycle, it should not ask, is the motorcycle red? So we followed Davidsonian formal semantics and made sure that VQA-based image evaluation should follow these 4 properties. Each question should be atomic, only asking one thing at a time. It should also be unique, right? It should not ask like there should not be multiple questions asking the same thing, because then you get multiple credit or multiple penalties. It should also have full semantic coverage of the prompt. But the most important part is the valid dependencies, because if I've already said no to the parent, right, is there a motorcycle? If that's already no, it should not ask questions on the descendants. It should not ask questions that have a parent-child relationship, right, with the parent question. So this is sort of one sort of complete sort of story, right, of how you want to go from visual programming for evaluation, but how do you need to take care of the VQA miscellaneous aspect? And then the second small example that I'll end with is DALI eval. So this was, like I said, the first sort of paper that tried to make image evaluation quantitative. Instead of just having FID, right, these distribution-based metrics. So the first part of this paper measures very fine-grained skills like counting, spatial relations, scale, and so on, which I'll skip. But the second part was on social biases. And we also red teamed with OpenAI. This was exactly the time when DALI 2, I think, came out. So we also red teamed with OpenAI on being able to evaluate these models. So the basic idea here is that you will have prompts like a person who works as a nurse. There can be thousands of such prompts with different professions. And if you're trying to test the bias of the model, on things like gender or skin tone or attribute. So if I take skin tone and as an example, you want to basically make sure that after doing illumination and lighting kind of corrections, if you calculate the skin tone on a monk skin tone scale of 1 to 10, right, of all the distribution of the generated images, if the model is less biased, then the distribution should be as close to uniform as possible, right? So this is basically the simple metric you can use, which is measuring the variance of distribution or the distance of the distribution from the uniform distribution. So how skewed are the distributions, right, in other words? And so some very high level results that I can refer to, and then we can discuss more. One was we showed that for very specific kinds of professions, like accountant and nurses, the bias was much, much higher for all of these models. The other interesting observation was that larger models, right, were much more biased than smaller models. Yeah, so a lot of the details are in the red teaming document with the DALI 2 from OpenAI and also in our paper. So let me conclude here. So just want to keep a minute for some of the conclusions and big challenges, and then happy to take questions. So I think the first bullet should be obvious by now, hopefully, right? So I discussed a lot of trade-off of like black box end-to-end pre-training versus this more modular paradigm, right? Where you basically want to have different kinds of experts, right, that are already good at what they do, but then can we find ways to actually make them generalize to unseen scenarios? Also do this interpretably and controllably, right, with human in the loop. And this also allows out of distribution kind of generalization. The second bullet is pretty important. I tried to cover as many modalities as I could in 55 minutes, but there is like much more, right, to be done. So just one simple example is non-verbal modalities like gesture and gaze, right? So through this education institute with NSF, we have actually a lot of work now on trying to also have classrooms where if you're trying to understand which part of the classroom was boring for the students versus interesting, right? There's a lot of other information needed about, are they shared collaboration through their gaze patterns? Are they actually interested in the class, right? Where are they looking? What's their posture? But even more important is action interaction, right? As humans, we learn a lot by burning our hand in something hot or banging our head against the wall and like learning, right, not to do that again. So the problem here is that we cannot throw these agents into simulated environments right now to learn all of this, because the simulated environments themselves, right, are very limited. We are the ones defining the simulated environments. So it's a very big chicken and egg problem, and one of the biggest problems, in my opinion, right now, where how do we create the best realistic environments in which we learned as kids, right, for these models to be thrown in and learn as agents. I also covered long distance video generation, but on the understanding side, we have a lot of work. And one big issue there is shortcuts. A lot of these models on long context are actually taking shortcuts and not really using the long context. So there's a lot of interesting work to be done on causality and counterfactuality here, right? Making sure that they're right for the right reasons, which means that if you remove something important, right, they should basically change their answer. But if you're removing something not important, right, then they should not change their answer. There's also more objectives for this, right? You also want to make sure that they can tell you why they changed their answer. So we have some initial work on this. I'll skip the fine-grained evaluation part. We covered a lot of that. Yeah, so the second and the third last bullets are very crucial. We did not cover this today, but happy to chat about it. So continual learning and unlearning, right? So one biggest problem right now is we cannot keep training these models again, right? When new information comes in or old information gets outdated. And also it's not just about outdated information. Many times that information is toxic or private, right, or unsafe. So there's a lot of interest and initial work now on something called model editing, right? How can we keep continually sort of updating the model? But that's also a very big sort of open challenge right now, because even localizing where the knowledge is stored in the model, right, is not easy. And if you use that localization information to edit the model, the problem is you have to make sure that you're not editing something that's causally unrelated, right? So technically you need a belief graph of all the beliefs of the model. And then when you edit one belief, you should make sure that all the causally related beliefs are edited, right? Whereas the causally unrelated ones should not be touched. So this is a big sort of trade-off here of like a lot of unlearning methods, right? Also killing or hurting information that shouldn't be edited. And then efficiency, we covered a little bit through unification, right? But there's a lot of axes here. There's time, storage, memory, carbon footprint, etc. So we have a lot other works on efficiency, which I'm happy to talk about. Specifically, one new area is something you might be interested in called model merging, where if you have two different task vectors, and you want them to be used for a new multitask setting for which there's no data or you don't have compute to train the model again for that task, can we directly merge the task vectors by taking interference into account, right? Some places they'll be clashing. So you find a way to avoid interference or resolve interference. And then there are surprisingly good results on doing model merging with interference resolution directly, right? Zero shot. So yeah, I'll end there. And thanks to all the students of the work that I presented. And we are hiring students and postdocs. So please chat with me.
Thank you very much for the very interesting talk. I was wondering when you were talking about something like TVLT, where you had like the like it was, I think that was the one with the video, right? When you were predicting like masking parts of the
audio spectrograms.
Yeah, exactly. So this might not be very smart, but like, is that something you could be useful for instance, compressing videos, or is the inference cost too much for something like that to be viable?
For compressing videos, yeah. So that's a very good question. So video compression, right, is a very old community which has actually used a lot of right ideas before that already existed, right? That now we are using in video understanding and generation. So one sort of main idea, if I remember correctly, is finding transitions in videos, right, where the main changes happen, right? Because then you can actually compress the information that's not relevant to the main right pieces of the video. So that's one usual approach. The audio-based approach, I'm sure people have tried in the compression community. There's a lot of work that has shown right how to use the audio to understand what parts of the video are important, right? Because that can be an additional modality to understand what is easy to compress. So maybe that's sort of a partial answer. But if you're saying how can our generative approach be relevant, I think I don't know if I understand that question exactly, but like one, I think simple way would be that if you have this pre-training sort of architecture here, the task, the pre-training objective itself could be teaching it, right, to predict which parts of the video to throw out. So yeah, it could be part of the pre-training, but I would be curious to see if this pre-trained model using fine-tuning or in-context learning can already do well at that task, because it's jointly right learning audio and video representations. So yeah, I mean, it's an empirical question, but I think it should learn some things because of this joint nature that I mentioned, right? The audio tells you which parts of the video are unimportant. So because it's training this through a joint encoder, hopefully it will already be good at that task, but it will definitely be pretty good with some in-context learning.
Okay, thank
like
you.
with a few examples.
Thank you for your presentation. I would like to ask if in the Cody any-to-any, if the formats of video and audio are preserved.
Sorry, what? Are preserved?
Yes, the formats. You lost some quality, you can keep the same.
Oh, you mean like in terms of quality? Yeah, so like I said, I mean, so I think there's no good definition of preserving because it's all being generated pixel by pixel.
Yeah.
So we don't really have any ground truth, right? These are all scenarios that are not in the training data. So the whole point of Cody is to generate unseen scenarios. But in terms of quality, yeah, this is only 8 A6000s or 4 A100s. So recently, I think a couple of months ago, another group took Cody and was able to show that if you scale it with many more GPUs, the visual quality is very high. Yeah. But yeah, I think to make your question maybe a bit more technical, like the answer more technical, is that yes, the main goal was to make the mixing of the right LDM latent variables. But yeah, in general, that mixing will always have some trade-off with the quality. That's why, if you remember, I said the very important part was that helps here, not solves it completely, is to train the individual modality LDMs first independently and then have the mixing. But there might be some nice solution to also have an ending like last step right? To bring them, maybe to bring back some of the unimodal, fine tuning back to bring each modality, right, to more quality. So we might also be able to end with some independent training and not just start with it. So there could be some curriculum learning here that could help.
I can add just one little thing. Right now, that is one of the few ways to detect that is, for instance, a fraud in terms of a voice, the voice of parents asking for money, because it's a little bit more robotized, like robot, and a bit slower than the actual voice. But
Okay.
the tone, the speech was already captured.
Yeah, I'm sure there's some nice like jailbreaking kinds of papers on this. Yeah, so we basically have focused mostly on audio, not speech, like rain sounds and train, like different kinds of, yeah, just in terms of making sure that can it do the mixing synchronously.
Oh, I have a question as well.
Yeah.
So, okay, thanks for the nice talk first. How large are these models in practice, like Cody, in terms of number of
So
parameters?
Cody was like a industry collaboration, but we still kept it pretty like medium scale. It was, I mean, I don't remember the exact, it's definitely in the paper, but yeah, so definitely not like 8 A6000s, like our video generation academic only effort, but also not like 1,000 GPUs, like some, like probably on the order of like 32 to 64 GPUs.
And how long it took to train the model?
Usually like a week.
Thanks.
It's been a while. I mean, I can check the paper. The hardwares keep changing. Like all our A6000s are already becoming useless. A100s are becoming useless now. But yeah, I can, yeah, we can discuss offline. Probably H100s, if I remember correctly. Great. Okay, yeah.
So I find it very interesting, this approach where you are representing all different modalities in a shared space, because this opens up a lot of new possibilities. How good do you think these models will be in imputing missing modalities, or being robust when some modalities are missing or noisy, which is something that happens a lot in practice, right?
Yeah. So I think that was one of the main goals, right? That there might be a lot of missing modalities in the training data. So a lot of these examples we are showing actually don't exist in the training data. So that was like one of the main motivations. I think one of the challenges currently, which is one of the next steps here, right, is that it's like, should we do this through diffusion models or autoregressive or other families? So if you look at the control adapter example, we've also extended this to like diffusion transformers, like this one, right? So that's sort of still not, I mean, perfect. But one sort of big challenge here is that, okay, the mixing is being done, but then if the video is very long, right, then the mixing also needs to take care of the alignment. So you can't just mix the audio LDM and the video LDM, but you also need to make sure that it's mixing at the right time steps. So we have short videos like the teddy bear example, but if it's much longer, right, then there will be some limitations of the diffusion model mixing. So then you can start going to diffusion transformers, or I mean, there's also, we are trying to think of like the sort of, if we can do all of this through autoregressive only. So that's sort of been one of, so then it will be interesting, like how much sort of missing modalities affects there.
Just another question. Thank you for the fantastic talk. It seems like in the later work you described, this planning or more layout pipeline goes a little bit against the idea that you learn just from data. You kind of like explicitly set up for what you want to test. Do you think this scales, or what is your take on how to take this further for more complex reasoning?
Learning only from data. Can you say a bit more?
Like for more complex reasoning tasks, it seems like either you test for whether it's up or down, or these more like simple.
No. So, but just to be clear, this is just some nice sort of physics examples. Like it's not only doing that, right? I mean, this is much harder than like up or down. If you look at all the actual examples on the website, like reading a book, holding on left hand versus right hand, So these are all like very sort of complex, like these are things that all current models like really struggle at, right? So, but yeah, I agree with your question. It's a very important trade-off. Like when you do this process, I mean, you always have to make sure that the constraints are actually not too strong. So that's one thing that partially answers your question, is that we actually ask the model to also try to learn itself when to have softer constraints versus harder constraints. Because if you make the bounding box or the plan constraints too strong, then it starts affecting the overall quality of the generated frames of the video. So there's this specific interesting trade-off here to make sure that it uses the constraints with only certain amount of importance, right? So that's an interesting open challenge right now.
And what about this compositionality of these constraints? Do you see this already in the models, or you think?
Yeah, so I think if we have some very, very sort of so we can handle a lot of out of distribution, but I'm sure there's some tail, right, where if it's something very uncommonsensical, yeah, I'm sure the LLM will also not be good at it. So I think if that's what you're getting at, yes, then there's still, I'm sure, a long tail of things that it will be limited to in terms of compositionality. I mean, one easy example would be, I'm sure it will like start dropping in performance if there's like 5 objects involved with different compositionality, right, as opposed to 2 or 3. But I still feel like the answer, I mean, scale will get us a long way there, but definitely not fully. And that's why I'm actually proposing the opposite. Right? I'm saying it should not just be data scale. It should be more reasoning capabilities, right, targeted for different reasoning categories, right? So not just, okay, let me add. So actually a lot of these examples, so this, I did not mention this, but this video generation has not been trained on any long video generation examples. This is only trained on single scene videos. Right? So this is all composing this into long, consistent videos without having any data because of the planning, right, input from the LLM.
Thank you.
Hello, thank you for the talk. I saw that you publish a lot of works in this new conference, the conference on language modeling. I'm curious about hearing your thoughts and your point of views about this conference.
It seems like I mean, yeah, I'm not one of the organizers, but I think Danchi is. She's a program chair, so she might be a better answerer. But I think it's a good effort, and I mean, I think it's basically following the iClear model, and so I think more venues are always good. Yeah, the longer answer I can give over beer.
Okay, so let's thank. Thanks, Mohit. And enjoy dinner and see you tomorrow early in the morning.